Earlier class we have seen the methods for hydrogen production, and we have also seen that if we use steam reforming process, then what are the process steps involved. We have seen the preliminary process, which is the feedstock pre-treatment process or preparing the feed, and then we have also seen that a optional unit which could be a pre-reformation unit is required if higher hydrocarbons are used for the reforming reaction. When it is steam methane reforming, pre-reformer is not desired. Now let us look at the main process, which is of steam reforming process. When feedstock used is methane, it is known as steam methane reforming, else it is known as steam reforming reaction. Now in this, the natural gas, a preheated natural gas along with steam at a pressure of 2 to 2.5 MPa is passed into the reformer, wherein there are catalyst filled tubes. In these catalyst filled tubes, so the grey colored ones, these are the catalyst filled tubes. Here the reaction between methane and steam occurs so as to produce the required syngas, and we get the reformate gas. Now a reformer, if we look at the reformer geometry, it consists of bundles of such tubes with length, it could be somewhere between 7.5 to 12 meters. Thickness of about 1 to 2 centimeter, and these tubes, they are filled with the catalyst along with support and promoters. What catalyst, that we will see little later. Now in these reformer tubes the reaction takes place. These reformer tubes are externally heated with various burners. So it is a box or tubular furnace wherein there are many burners which heat the reformer catalyst filled tubes, and these burners could be arranged in various geometries. So either the furnace could be a top fired furnace wherein the burners are located at the top. It could be either the terrace fired reformer wherein from the sides the burner are heating the catalyst filled tubes. It could be from the walls, these burners location could be on the walls so as to heat the catalyst filled tubes, or it could be bottom fired reformer where the location of these burners is at the bottom. However, the major, irrespective of whatever is the geometry, these tubes, they are carrying catalyst. The process is natural gas, preheated natural gas along with steam passes through the reformer tubes which are filled with catalyst, thereby producing syngas. In this process, if it is methane, in the steam reformation process, methane acts as both feedstock as well as fuel. So methane is both feedstock and it is also fuel. So it is used for burning in the burners. So the fuel air mixture, it is passed through the burners, the fuel and air mixture, it combusts in the burners, different burners, providing the required heat which is being utilized for the reaction to take place. Now what is that reaction, we will see. One more thing to be mentioned here is that the combustion product, so herein methane burns to give the desired heat. However, it is not 100% heat transfer to the reactor filled tubes. The combustion gases carry the remaining heat, and these gases still have, these are hot and have high grade heat that can be utilized in heat exchangers for either preheating the natural gas or for steam production. So, there could be, after that there could be a heat exchanger which can extract the heat which comes out with the combustion gases to either preheat the mixture or to generate steam. Now, let us look at the process of steam reformation. If we look at the process of steam methane reformation, methane reacts with steam producing syngas. So, very simple reaction, methane which is feedstock reacting with the oxidant to produce syngas. Now, couple of things to be considered here is, one is this sign. So, it is an endothermic reaction. So, the process of steam methane reforming is an endothermic reaction. The value suggests that it is highly endothermic reaction. At the same time, if we see 1 mole of methane reacts with 1 mole of steam to produce 4 moles of the product. So, as such, by Le-Chatelier's principle, there is an increase in volume. So, the reaction is favored at lower pressure. So, the desired conditions for operation of this reaction is high temperature and low pressure. Now, the reaction takes place at temperatures of 850 to 900 degrees centigrade in the reformer tubes. However, the pressure desired as per the reaction conditions, thermodynamics is low, but most of the applications wherein the hydrogen will be used, they require hydrogen at a higher pressure. At the same time, if we increase the pressure, the size of the reactor will be reduced, at the same time there will be a better throughput. So, as such these are operated at a higher pressure. So, usually somewhere around 2.5 to 2.5 MPa it is desired to operate. Reformers, they operate in this particular region. Now, this high temperature poses certain constraints. One is the reformer metallurgical constraint for the reformer tubes, it should be stable under these high temperature and pressure conditions. So, these are to be made up of special material, but in actual practice this reaction is operated under high steam to carbon ratio content. So, the operation condition are, we keep high steam to carbon ratio. The reason for keeping this high steam to carbon ratio is the coke which causes deactivation of the reforming catalyst, that reaction is not favorable when we use high S by C ratio. So, the coke deposition which can lead to deactivation and several other challenges, it can deactivate the catalyst, can deposit onto the surface of the catalyst, reducing the active sites, can create hot spot because of that. At the same time, the deactivation of catalyst can lead to higher tube wall temperature. The pores within the catalyst filled tube can get filled. So, the voids get filled, thereby reducing the flow of the gases, and it can be the increased tube wall temperature can also lead to the tube failure. So, in order to avoid all those, a high steam to carbon ratio is preferred in this particular reaction. So, what is desired is a high temperature, although desired is a low pressure, but usually these reforming reactors are operated under pressure conditions, higher pressure conditions, somewhere around 2 to 2.6 megapascal and a higher steam to carbon ratio. Now, as we have seen that in the process of reformation, there is a catalyst deactivation problem which could be seen, and this occurs because of a wide number of reasons. So, the reasons for catalyst formation are several other reactions like the decomposition of methane can result into formation of coke. So, methane can decompose to give carbon and hydrogen. Delta H for this process is 74.6 kilojoule per mole. Another reaction which can lead to coke formation on the catalyst is disproportionation of carbon monoxide. Delta H, corresponding delta H for this reaction is that can also result into the coke formation. Now, if we see in the reformer tubes what is the major regions where coke could be formed. So, majority of this coke formation occurs in the, either it can occur on the inner tubes, inner wall of the tubes, or it can occur at the top of the tubes on the front region. So, the majority of the carbon occurs in the front region of the tubes, and there are various reasons for it. If we see what are the major reasons, one is at the top of the tube the hydrocarbon concentration is highest. However, the equilibrium is low at that region. The system has not reached equilibrium. So, equilibrium conditions are not maintained. However, the hydrocarbon concentration is high at that place. The reaction rate, so at the top of the region the reaction rate is slow. However, the heat flux is high. So, as such there could be the carbon deposition that can occur onto the catalyst. Now, what this carbon being formed in the various reaction does? It deactivates the catalyst, which can result into excessive tube wall temperature. Tube wall temperature increases, it can lower the pressure, it can even lead to tube failures. It can block the porous medium which is there in the reformer tubes. Now how can we take care of this carbon formation? One way, as we have seen, to increase the steam to carbon ratio. Now there are, if we look at the entire process, thermodynamics of the process, we see that the carbon formation, it is preferred for temperatures less than 600 degrees centigrade. So below this region, the thermodynamics prefers carbon formation. So usually the reactions, that is why the reaction steam methane reforming, it is usually a high temperature process and the reaction occurs at 850 to 900 degrees centigrade, under which the coke deposition is lower. So steam to carbon ratio is the best way to reduce this coke formation. One more method could be wherein we can use promoters. So either different promoters could be used along with catalyst. These promoters, so we will see in the later that both catalyst, support as well as the promoters added, they play a dominating role in the reformation reaction. These promoters provide the required basicity to the catalyst, because acidic surfaces, they are more prone to the decomposition of methane. So they provide the required basicity so that the carbon which is being formed undergoes the gasification reaction. So this carbon can undergo gasification. This is a method by which we can remove the carbon formed. In fact, there are two competing processes which are going on, the formation of carbon through any of these processes and the removal of carbon by means of carbon or coke gasification. So these are two competing processes. However, at temperatures beyond 600 degrees centigrade, the gasification will dominate or the carbon deposition will be lowered. Now once after the steam methane reformation reaction, the next step which is being considered, which is the water gas shift. Water gas shift reaction is carried out after the reformation reaction. This is done so as to increase the yield of hydrogen. In this process, carbon monoxide which is formed, the syngas which is formed in the reforming step, the carbon monoxide component of it is being converted into carbon dioxide. At the same time we are getting more of hydrogen. However, the reaction is an exothermic reaction. So carbon monoxide in the presence of excess of steam, again the reason of excess of steam is to reduce the deactivation of catalyst, it gets converted into carbon dioxide and hydrogen. So from the value of delta H, we can see that it is an exothermic reaction, slightly exothermic reaction. That means it is favored at low temperatures. Usually the kinetics of reactions we know that are better at a higher temperature. So there is a trade off. To keep higher temperature and having so the reaction will be, so in that case it could be favor a backward reaction. In if we keep higher temperature. At the same time, if the temperature is lower down, then the reaction kinetics will get slower. So, this is a trade off that we have to, that need to be looked at, although it is being favored at a lower temperature. Now, in this particular process, since the temperature required is lower, after the steam methane reforming process, wherein the exhaust gas comes at a higher temperature, which is roughly about, the reaction occurs at 850 to 900 degree centigrade. Around that the exit gas leaves the reformer unit, it has to be cooled down in a cooler, intercooler, before it enters into the water gas shift unit. So, it has to be cooled down to the desired temperature. Now, what is that desired temperature? That depends whether this water gas shift reaction is being carried in one unit, high temperature water gas shift alone is being considered, or both high temperature and low temperature water gas shift reactions are to be carried out. Now, what will decide whether it is only one step we have to do after the reformation or two steps, that is determined by the purification step. So, the purification step will tell, for example, if it is, the purification is using pressure swing adsorption method, then only high temperature water gas shift is good enough. However, if it is solvent based removal method, purification method, then both high temperature as well as low temperature water gas shift are required to reduce the carbon monoxide levels in the gas stream, in the outlet stream from the reforming unit. So, depending upon the final purification step, whether it will be high temperature water gas shift alone like with pressure swing adsorption unit, or whether it will be high temperature and low temperature water gas shift both, if it is solvent based cleaning, removal of carbon dioxide followed by methanator to get pure hydrogen, the water gas shift will be, setup will be different. In the high temperature water gas shift, the reformate gas which is obtained from steam methane reforming, it has to be cooled down to a temperature of 350 degree centigrade. So, the reformate gas was at 850 or 900 degree centigrade from reformer. After the reformer has to be cooled down to 350 degree centigrade, and thereafter it is reacted. The carbon monoxide reacts with steam to give carbon dioxide and hydrogen. The catalyst which are used are magnetite, iron catalyst, which is with chromia, and this reduces the carbon monoxide content to about 2%, depending upon what is the feedstock. It is finally reduced to 2 to 5% after the first water gas shift reaction. Now, in this high temperature water gas shift reaction, depending on the feed composition, the temperature could be somewhere between 350 to 500 degree centigrade. Conditions are 350 to 500 degree centigrade, pressures of 20 to 30 bar, the gas hourly space velocity of 400 to 1200 per hour, with a residence time of somewhere around 3 to 9 seconds, and finally it could reduce the carbon monoxide content to 3 to 5%. However, the low temperature water gas shift, the next step with solvent based removal method is the low temperature water gas shift. This can further reduce down the carbon monoxide content to less than 1 volume percent. So, carbon monoxide content is somewhat around 2.2 to 0.4% after this step. In the low temperature water gas shift reaction, the catalyst used are zinc oxide, copper oxide on alumina, and the reaction takes place in the temperature range of 220 to 250 degree centigrade. So, after the high temperature water gas shift, further the gas needs to be cooled down for the low temperature water gas shift. Under these conditions, the carbon monoxide content reduces to 0.2 to 4%, the pressure is around 10 to 30 bar, the gas hourly space velocity is somewhere around 3600 per hour. Now, in the high temperature water gas shift, the benefit of faster kinetics at a slightly higher temperature is being taken care of. However, the low temperature water gas shift is used to further reduce the carbon monoxide content to less than 1%. Next we will be looking at what are the different purification steps for getting pure hydrogen. Thank you.